Welcome to this operating systems video about threads. So I've created a new folder to start a new project, and I've created a git ignore that ignores the a.out and any other executable files. And then I've created this simple program that is the main. It will take in one command line argument, which is the number of iterations or number of times that we want to call this do math method. So it just goes in a loop and it calls the do math method that many times. All the do math method does is add 1 to sum 100 times. And if you notice, sum is a global variable. And at the end, we'll print it out. Okay, so we'll go ahead and I've already compiled this and we'll go ahead and run it. And the sum, since we're doing it 4 times, we're calling this do math method 4 times, it should be equal to 400. And sure enough, doing math 4 times, and we get a total of 400 added to our global variable sum. So now we have a multiple core CPU, meaning that we can run multiple programs at the same time, or we can run multiple threads at the same time. So maybe we can run this program faster if we launched a thread and each thread did this method 1 time. So now instead of calling do math 4 times, the main thread will launch 4 threads, and each thread will do this do math function 1 time. And we should still get the same answer, but now we'll be calculating our sum at the same time and hopefully be able to get our answer quicker. Now, before I go on and show you how to launch up threads in C, I just want to hope that you've read the book on threads and realize that threads could be very helpful. For instance, we can have a main thread that listens to the UI interface, like moves the mouse and as we type makes the characters show up. Or even if we're on a mobile app that listens to like the finger swipes and stuff, so the user doesn't think the app is locked up. And then we can have a background thread that's downloading a picture, or another background thread that's in charge of saving something to a file, or another background thread that's sending a request over the internet. And we don't want if we had them all in the same thread, then say downloading a picture or saving something to a file would lock up our user interface because our program is busy downloading something, and our interface would be locked up and we couldn't interact with it. So there's several different other reasons that we'd want to launch threads. In this case, we just want to take advantage of a multi-core CPU to be able to do operations together instead of have to wait for just one single thread of operation to go through. So I've included the pthread library, which will allow us to launch up threads. And I'm also creating an array, or at least a pointer to an array of these pthread structs. And those are going to be a handle to our thread. So when we launch a thread, we need a way to communicate, or a name to name that thread. So I'm going to create an array of threads so I can communicate with the threads that I launch up. And so after I figure out how many times or how many threads I need to create, then I'll go ahead and use calc and create that array of structures on the heap. And then we're going to launch a certain number of threads, and this pthread create is a function that will launch a thread. So let me go over the parameters. The first one is the memory address of where we want to store that handle. Now that again, the handle is a way so that I can communicate with this thread after I launch it. Next is our attributes, and we're just going to use the default attribute, so I'll just do null here. The next is the method that thread that I'm going to launch up should run. So it's the address of the do math method. Now, if you notice, I had to change the signature of the method so that it returns a void star, and it also takes in a void star as input. So what is a void star? Well, that's called a void pointer. And it's basically a pointer that can point to any type, because all pointers are the same size. We just put types in front of pointers to help the programmer make sure that he points the pointer at the right thing. In this case, it can be a pointer to anything. So this just allows the method that we're going to call to be able to take something in for input, at least a pointer, and return a pointer as its output when it finishes. But in my case, what I'm going to do is I'm going to take this I, cast it to be a long, So now we have it in a long, and that's going to be the same size or the same number of bits that it takes to store a pointer. And then I'm going to cast that long into a pointer. So I'm just, let's say the I is 2. So basically I'm creating a pointer that points to 2, but I'm not going to use it as a pointer. I'm just going to use it as a number. So the pthread create, if it returns a 0, everything was successful. If it doesn't, then perr will print out an error message. And then at the end, we're still going to do that. Now down in my function, again, the signature has changed. I'm going to take the argument that was passed in, cast it from a pointer back to a long, and then I'm going to cast it down to an integer. So now I know what thread I am. And notice that the thread will change each time through the loop. I will be one number greater, so I'll be able to know which thread I am. And then I'll just go ahead and add 100 to each number. So that's the way that we will launch up threads, this pthread create. Now we do need a structure to, or a handle to be able to reference that thread and communicate with it. And that's what this threads is there. Okay, now because I'm using the pthread library, I need to include that library as I compile it. And that's with the -L and then the name of my library. And that's because there's lots of libraries to link to. So we need to, for pthread, we need to call it out specifically so that we can link this pthread library in with our executable. So make sure you include that -L when you compile your programs. And then we'll just go ahead and run it, and we'll do 4 at the same time. Now we see, oh no, our sum's 0, and it launched 4 threads. We didn't get any error messages, so what is going on? Well, the problem is our main thread, which is the thread that's running main, it'll keep running, it'll launch 4 threads, and it will just keep running and exit the main method. Now, whenever the main thread quits, that means our full program quits, and it kills off any other threads that it might have launched. So we did launch threads, we just quit so fast that we didn't let any of those threads run. So now to fix that problem, we don't want our main thread to exit and kill all the other threads until all the other threads are finished running. So that's what pthread join will do. As you can see, the man page says it waits for the thread to terminate, and that if it's already terminated, then it'll just return immediately. So if I call this, and the thread that I pass in here is still working, I'll wait until that thread dies. If the thread's already died, then I'll just move on to the next one. And this will make sure that all the threads have finished before I continue on. So we'll go ahead and recompile our program, and now let's run it. And we're back to our sum being 400, but now we're able to do those threads all at the same time. So theoretically, this should run faster than the other way. My guess is it's not actually going to run fast because adding 400 to a number is fairly quick, whereas launching up a thread does take a little bit of time and overhead. So I bet in the overhead of launching the threads has actually slowed this down. But if we're doing something more complicated than just adding 1 to sum 100 times, then launching up threads certainly would increase our performance. There is one problem though, is sum is a shared variable. All of our threads, including our main thread, have access to sum. So hopefully you remember from reading in the book about threads that each thread has some memory that they share with all the other threads, and then they have their own memory that they keep to themselves. Now the stuff that's shared are any global variables, which includes this sum. So it's global, all threads can access it. The other thing that it can share is anything we put on the heap. But anything that's on the stack is what the thread owns itself, and it doesn't have to worry about other threads messing with its stack. So each thread has its own individual stack, but the global address space, which are global variables, and our heap are shared between all of our threads. So this sum variable that we're adding 1 to is shared between all the threads, which makes sense. That's why we got 400. But let me do a little bit of work to make this an error that could happen randomly a little more apparent. I'm going to force this error to happen. So now doing sum plus plus is actually doing something like this. We're reading the sum value and storing it in a register for that thread. Then we're adding 1 to it, and then we're taking the result and storing it back in sum. So we have to pull the value out of memory and put it into a register to be able to do this. Then we can change the value, and then we have to put it back in memory. So this just makes that process a little more apparent. But that was still, this thing is still happening even though I just do sum plus plus. Now, there's a small chance that something might happen while in between reading this value, adding 1 to it, and writing it back. The thread could could get kicked out of its running mode, so it could get put to sleep temporarily. Now here I'm forcing the thread to sleep so that it happens, but there's still a probability that it could happen. I'm just kind of forcing it to happen here. So let's see what happens when our threads just decide to sleep after they've read their value, but before they've written it back. And by the way, to use that sleep method, we do have to include the uni standard library. And I also believe I might have forgotten a semicolon after I declared temp. So let's go ahead and run this and see our result after I've compiled. And you can see our sum is 106. Now that's weird. The sum should be 400. Why is it 106? And hopefully you've realized that as one thread read sum and it went to sleep, another thread was able to increment and write sum back. But then the thread wakes back up and it doesn't reread that sum value that's been changed. It adds 1 to it and then overwrites what another thread did. So now we have a race condition. It depends on the order of the threads and how fast they're able to write that back. Now, the chances are a little bit low, but if you have a program, say on an iPhone or an Android phone or something like that, and you have this error and you got millions of people using it, I guarantee you someone is going to have this error, and now they're going to wonder why math, it doesn't work on their programs anymore. So we need to fix this problem to make sure that sum is only accessed by one thread at a time. So now we have the SemiForce library, and hopefully you've read about SemiForce from your book as well. And they're they can act as mutexes, but they're also counting SemiForce, so we can set their value and allow more than one thread through, but we're not going to do that here. But we'll go ahead and declare a SemiForce, and we'll call that SemiForce sum lock. And so here I'm initializing the SemiForce. Right now, that's just some memory that's been uninitialized. So SemiNit will initialize it. So first of all is the address of where the SemiForce is located. The next one, we're going to put 0 there. That's if we want to share our SemiForce with another process, not another thread. So we just have one process, so we'll just put 0 there. And finally, we have this number 1, meaning that allows one thread to go through at a time. So the way this works is SemWait waits on the SemiForce. So if that value that remember we initialized it to 1, every time you call SemWait, we'll decrement that value by 1 until it gets to 0. So the first thread that gets to this point we'll call SemWait, and that'll decrement the value of the SemiForce to 0. And threads will go ahead and go through, it'll sleep, which will probably allow another thread to call SemWait. But it will see that the sem lock or the SemiForce is at 0, and it will have to wait until that number gets incremented. So how does it get incremented? Well, the thread that slept will hopefully wake up. And so this is 5 microseconds that it will sleep for. It'll wake up, finish its operation, and then it will post to the SemiForce, and that will increment it by 1, allowing a thread that's waiting for the sum lock to go through this area right here. So this is our critical section, and we're enforcing mutual exclusion by using our SemiForce. So one thread at a time will be allowed to enter and do this operation. After it's done, it'll post, which will allow another thread to go through and do the same operation. And that'll synchronize all of our threads so that hopefully we'll get the right answer when we're done. So recompiling and running, we'll see we're back to getting the right answer of 400. Now, the difference between a mutex and a SemiForce is a mutex can only be 1 or 0, whereas a SemiForce, they're often called counting SemiForce, where it can increase the value higher and higher. So we could initialize a semaphore with the value of 5 or something. And that'll allow 5 threads to go through before they're held up. And that works really well if we have, say, a buffer that only has 5 slots. That'll allow 5 threads to go through and fill up one of the slots in the buffer. Once the buffer is full, the semaphore will prevent another thread from adding something to the buffer. And then as we take things off the buffer, we can post to the semaphore saying, hey, there's a free spot, and that'll allow another thread to take the spot that was freed up. So these content semaphores are a little bit more powerful than binary semaphores, or another name is mutexes that can only have a 1 or 0 value. But make sure you set this second argument, not the first one. It has to do with sharing the semaphore with other processes, which is a more advanced thing that we won't do in this class. So as a final note, I do have a memory leak in this program because if you notice, I create these pthread structures on the heap and I forget to give it back. So it's my responsibility to give the memory back to the system to free up my memory. So I do need to call free threads before my program quits. So recompiling and running, you can still see that it works fine. Now, a memory leak in this program probably isn't that big of a deal, but if this were a server or a program that had to run a long time and that ended up creating these thread structures a lot, then eventually we'd run out of memory.